Hi, everyone. A few things here at the beginning. Remember that you have a homework set due on Friday. Okay, so that is Friday, the 3rd of April. That will be your last homework set from Chapter 8, and we'll finally have homework sets from Chapter 9. As of right now, I'm surprisingly starting to catch up on the schedule, but I still think that my goal is going to be basically to get through Chapter 9. My capstone seminar will cover the material in Chapter 10 again anyways. If that's something that you'll be around to take, I would encourage you to take that. Combinatorial game theory just kind of takes all of this stuff a step further. And if this is material that you have enjoyed, then I really think that you would enjoy that as well. There we just concentrate on games that are called progressively finite. That simply means that there's typically just two people playing, and they alternate moves, and every single move makes progress towards termination of the game. And typically you require that people, or that one of the two people has to win. So the game doesn't end in a draw. There are ways to tweak games like tic-tac-toe so that happens. So you can kind of do unmoves once you end up with a cat's game in tic-tac-toe. Or I won't get into the details of what that means, but it is possible to turn tic-tac-toe into a so-called progressively finite game. Students really tend to enjoy that material. So I'm going to leave that for another day, I think. So I really do just want to spend a fair amount of time really trying to understand all the details in Chapter 9. So hopefully that will be time well spent. Polya's enumeration formula is incredibly powerful, and it really is kind of a climactic result given the sorts of things that we've been studying. So that's the goal, is to finish Chapter 9. That will change the homework set schedule. I'll keep you apprised as to what I'll be expecting you to turn in. But my overall suspicion is that it will be quite a reprieve for you, which I'm sure will be welcomed. I'm sure that you have a lot going on over these last few weeks. So I just want to give you a chance to get caught up and really just enjoy this material. There's no reason to really speed through it. This is just good stuff, and let's just enjoy it together. So don't forget to come and ask questions tomorrow during office hours or class if you have any remaining ones on this latest homework. I'd be happy to address those with you. You should be able at this juncture to start working on the next homework set also. Unless otherwise specified, you could basically take it to the bank that will be due about a week from Friday also. Okay, we'll just kind of keep moving ahead that way. All right, let's look once more at Burnsides theorem, and my goal today is to simply work through a number of examples that shows just the utility of this result that we proved together last time. Here was the statement of Burnsides theorem. Again, I want to be mindful of this lecture of not of not talking for 100 minutes like I did last time. Got a little bit too excited as we were going through Burnsides theorem. We got through it all though, so we can actually start using it in a lot of different contexts now, and I think you'll really enjoy some of these applications. But I just want to remind you that this is the statement of Burnsides theorem right here in all of its glory. Okay, and one thing that was kind of interesting was the fact that G was just a group of symmetries on the colorings. Remember, we were using capital N to represent the number of equivalence classes of colorings under the symmetries of G. Okay, and that was the thing that we really wanted to count, because those were the colorings that were truly distinct once we allow G to work its magic on all the different colorings in T. So T was the collection of colorings of whatever object it is we were looking at. Remember that phi of C is the number of permutations that leave a coloring fixed. Okay. So you give me a coloring, and I go and search for all of the permutations that happen to fix that coloring, don't really change it at all. And phi of C is the number of those permutations. And we figured out that by kind of writing that sum as a double sum and using indicator functions, it was possible to also write that sum as a sum over permutations in the group. And we had this function psi of pi, which is the number of colorings fixed by pi. All right, so it's the total number of colorings fixed by pi. Sometimes it's easier to work with that version of it. So rather than having to think about fixing a coloring and counting the number of permutations that fix it, here we're fixing the permutation and counting the number of colorings that it fixes. Turns out that that is going to be extremely needful for us later on in applying Burnsides theorem. It's much, much easier to think about the psi function than it is the phi function. Okay. I want to share with you kind of a picture proof of Burnsides theorem that's not in the book, but it's just something that I have found to be extremely helpful in kind of keeping this whole picture in my mind. So I want to show you that next. All right, so here's a picture that I like to think about when I'm thinking about Burnsides theorem. So let me just talk about some of the specific things that are in here. First of all, I've taken all the colorings and which are represented by the set T, and I've actually taken all of the equivalence classes of colorings under the operation of the group on these colorings. I get the equivalence classes. That's what I've labeled by EC1, EC2, all the way through EC sub n, right? Don't forget, okay? Don't forget that n, remember what's capital N? N is equal to the number of equivalence classes. The number of equivalence classes, okay? So that's why I know that this thing stops at capital N. Remember that Burnsides theorem is trying to simply get a handle on how to compute what N is just based on things that we can easily extract from the situation we face. Now, just for convenience, I have up here said, look, I'm just going to concentrate on the first one of these equivalence classes. By the way, E sub C1 means the equivalence class containing the coloring C1. So E of C1, let's just say E of C1, let me write this. E of C1 is equal to the set of all C belonging to T such that C is equivalent to C1. And you know that being equivalent to C1, right? So let's kind of write this where C equivalent to C1 means that there exists some permutation in the group such that what? Pi, and remember we've been doing this crazy thing where we apply the permutation on the right, so pi of C is equal to C1, right? So pi moves us from C to C1. So by definition, two things are equivalent if and only if there exists a permutation that moves us from the one coloring to the other, okay? So obviously, I mean, so note the following. Let me just write this here. Note, of course, C1 belongs to E of C1, okay? That's just the reflexive property of the equivalence relation itself. C1 is equivalent to itself, so it's in there, okay? So I've just written down all of the equivalence classes here, And by the way, T, let me just write this. We did this in the proof also. T is equal to the disjoint union of these things. Okay, T is equal to the disjoint union of these equivalence classes. Okay, that's pretty clear, just the way that we've set it up. And then what I've done is I've zoomed in on the first equivalence class, just so we can get a handle on what's going on. I've straight up zoomed in on the first equivalence class, and that's what I've kind of expanded outward over to there, right? So let me just, I've kind of just zoomed in and expanded this out, right? I've expanded this out like this, just so we can take a look at what's happening. And then what I've done is I've listed all of the colorings that happen to be in E of C1. Okay, so I have C1 itself, which I'm going to call C1 with a superindex 1. Okay, and then C1 with a superindex 2, that's the second coloring that happens to be in there. C1, the reason I'm using superindices is because I've already used subindices over in the equivalence classes themselves. It would be confusing if I said C2 because I've already used C2 as kind of the representative coloring of the second equivalence class over there. So C1 superindex 2 is the second coloring in that equivalence class, C1 superindex 3, etc., all the way down to C1 superindex S. Okay, and that might be kind of weird, but the reason I'm using S is just out of convenience, right? I've kind of said, let the size of E sub C1 equal to S. So I know there's going to be S colorings in here, S colorings. So S is the size, right? S for size of that equivalence class, okay? And what we showed, if you will recall, is that each one of these colorings, okay, so each one of these, so like take C1 for instance, how many permutations fix C1? Okay, well that's what we called phi of C1. So phi of C1, if you will recall, let me just use purple right here. Okay, purple, phi of C1 is equal to the number of pi in G such that pi of C1 is equal to C1, okay? So phi of C1 is just the number of permutations that fix C1. Okay, so that little red circle I'm putting right there is I'm saying, I'm drawing those green arrows to indicate permutations that are cycling me back to C1, right? It doesn't move C1 anywhere. And there are phi of C1 of those. But we also proved that the number of things that move me from C1 superindex 1 to C1 superindex 2, the number of those is phi of C1 also. There's the number of things that fix C1 is the same as the number of things that move me from C1 superindex 1 to C1 and superindex 2. Okay, so that's what I'm kind of writing on the inside right here. Let me just kind of circle it in purple right here, right? So this thing is just simply saying the number of things that move me from C1 superindex 1 to C1 superindex 2 is phi of C1. And similarly, like it doesn't, like, no matter what I do, the number of things that move me from C1 superindex 1 to any of the C1 superindex i's is always phi of C1, okay? And so what I'm doing is I'm applying all of the permutations of the group. All of the permutations of the group are accounted for in those green arrows. And by definition, I'm going to hit every single one of the colorings, okay, in this equivalence class of C1. Otherwise, it wouldn't be in here. There has to be, for it to be in here, there would have to be a permutation that moves me from C1 superindex 1 to C1 superindex I for all I. So every single permutation is accounted for by one of those arrows. So let me just say right here that each green arrow is a permutation. okay, or represents. Okay, let me just say, you know, I want to be precise with my language here. So it represents a permutation. Represents a permutation. Okay. So if there are phi of C1 permutations that send C1 to itself, then there are also phi of C1 permutations that send me from the first coloring to the second in this equivalence class. And there are also phi of C1 permutations that send me from the first to the third, etc., all the way from the first coloring to the sth coloring in this equivalence class. There are phi of C1 permutations sending me from the first one to any one of these things. And that accounts for the entire group. And that's why we get this formula right here. Okay. That the size of the group, I've accounted for every single element in the group. The size of the group is equal to phi of C1 added to itself, a total of S times, right? You know, the number of things that send C1 of superindex 1 to itself is phi of C1, and the number of things that send C1 of superindex C1 superindex 1 to C1 superindex I for any I is also phi of C1. So I'm going to have S summands of size phi of C1, right? So that's why you get that the size of G is equal to the size of the equivalence class times phi of C1. But another way to write that, and this is kind of what we did, is we said the size of G is equal to, let me write it this way, the sum over all colorings in the equivalence class, E of C1, phi of C. Okay, after all, it's also true that if I take any one of these colorings, okay, how many things are there, like C1 superindex 3, for instance? How many things fix this thing? How many things fix this? How many things fix C1 superindex 3? Well, it's also going to be phi. It's also going to be phi, right? So it's obviously phi of C1 superindex 3. But you know that that's also going to just be phi of C1. Again, all of these have the same size. The number of things that fix this particular coloring is equal to the number of things that fix the first coloring. There's just a massive amount of structure going on in here. Okay, so this thing, right, I have this situation going on here. So no matter which coloring I take in the equivalence class, phi of that coloring is the same as phi of C1. So right, it doesn't really hurt us to just take any coloring in this thing, take any coloring in the equivalence class and just add up its phi. And that's going to automatically add phi of C1 together, a total of S times, just like it did if I was only concentrating on the permutations moving the first coloring to the other ones. Okay, and this really is kind of the all-important formula right here, because it's only a short step to Burnsides theorem. Okay, so let me pick out a, let me write the rest of this thing in blue. So first of all, T, we already said that T is equal to, I'm not going to write that again, actually. Down here, we said that T is equal to the disjoint union of these things, okay? That T is equal to the disjoint union of these things. So watch this. If I took the sum I going from 1 to capital N, we already did this before, but I just want to go through this again. Sum of C belonging to ECI, right? There's nothing different about this sum. This would be phi of C, okay? Well, what is that going to be every single time? And this is basically what Burnsides theorem says. This guy right here is going to be the size of the group. You're going to get the size of the group over and over and over again, and that's going to happen a total of n times. This would be n times the size of G. Okay, but on the other hand, what is this equal to? Well, if I just take I going from 1 to n and I take I sum over all colorings in the equivalence classes, that's just like summing over all colorings. So this is really just sum over all colorings, period. It makes no difference that I split it up over those equivalence classes. Sum over all colorings, phi of C. Okay, and that's where we get Burnsides theorem, namely that phi of C in T, phi of C is equal to, well, actually, let me put 1 over the size of the group over here, 1 over the size of the group over here. This is equal to n, okay? And that is the ultimate result that we ended up with. There it is, right there. That's what Burnsides theorem says. So this little picture right here, I think, is kind of helpful. You think of the colorings as split up into equivalence classes. You blow up one of those equivalence classes and look at it specifically, and remember that we had all of this structure in here with the number of permutations that fix each coloring. That number is always the same, so we just call it phi of any one of the colorings in the group. And then the number of things that move any coloring in equivalence class to another coloring in the equivalence class is also phi of any coloring in that group. And therefore, I get the size of the group by simply just adding together all of the phi of C's in the equivalence class. That is the key to Burnsides theorem, okay? All right, so that's a nice little picture argument that summarizes everything that we've done so far. I thought it was worthwhile to just kind of talk that through carefully again. So we really have fully explained ourselves again, just in that little picture back there. Some very nice combinatorics going on there. I think that picture is pretty helpful. I would recommend that you would kind of practice drawing it and really trying to understand every single feature in it. Anytime you have a visual way of explaining one of these combinatorial facts, that's always a nice thing to have in your cognition and in your tool belt. So we really have fully explained this Burnside theorem, which is really going to be the key to understanding everything else in this chapter. But one thing I wanted to kind of remind you of again is how it is we're able to go back and forth between these. I don't want to spend a lot of time talking about this, but remember what we did is we said that sum over colorings, phi of C. Now remember, phi of C is counting the number of permutations that leave the coloring fixed. So what we can do is we can use an indicator function in this way. We can say, well, I'm going to sum over all permutations in the group, and every time I have a permutation that happens to fix C, I want to count it. So you use the indicator function. That's going to be 1 whenever pi of C is equal to C, and it's 0 otherwise. So it's fairly clear that this right here, that sum, is just kind of a funny way of writing phi of C. But then you reverse the order of summation, and you write this as the sum over pi and G, sum over C and T, the indicator, pi of C equals C. And it's fairly evident that all this is going to count is the number of colorings that pi fixes. And that's exactly how we defined psi of pi, right? So that's how we get that sum over there is just the same as summing over permutations in the group psi of pi. Okay, and now we've really kind of reviewed stuff. We have a sort of clear visual picture of what's going on. Burnsides theorem should be really, really clear to us now. I hope it is. So there it is. And one thing that I want to point out, and we're going to use that now to our advantage. One thing I really want to point out is the following. All we needed was a bunch of colorings of some kind of geometric object. And we needed a group of symmetries on that geometric object. And as long as we can reasonably count the number of things that fix those colorings, or the number of permutations in the group, or the number of colorings that a permutation happens to fix for any given permutation in the group, then we're going to be able to use Burnsides theorem to count the number of truly distinct colorings under the group. All it needs to be is a group, though. And remember, all a group has to satisfy is it has to have an identity element. It has to be closed. That is, if I operate any two of them together, I get an element in the group still. And I have to have inverses, right? So anytime I have a permutation, I need to have its inverse in there also. So what's interesting is I can restrict the group that I look at. Okay, so it could just be nothing, none of this relied on G being like all possible symmetries, okay? All it has to be is a group of symmetries. It's incredibly freeing because I can look at the same situation and kind of reimagine the group that I'm going to allow to operate. Okay, so that's what I want to do next is first kind of use it in that context. And hopefully it'll be clear to you why I'm excited about this. Okay, here we go. Here we are again with our trusty example. I want to explain a little bit what I'm thinking about here. So remember, pi 1 was the identity, pi 2 is 90-degree rotation, pi 3 180, pi 4 270, pi 5 reflection across the vertical axis, pi 6 across the horizontal, pi 7 across the -1 slope, and pi 8 across the +1 slope. Okay, and doing this, I won't repeat the computation, but at the end of last time, we were able to use Burnsides theorem to get 6 just based on these permutations. We got, we went 1 over 8, and then we basically counted all of the various phi of colorings or psi of the permutations. But what if, okay, so let's just say, what if G was just equal to pi 1, pi 2, pi 3, pi 4? Okay, that is still a group, right? So in other words, these are just the rotations, okay? And of course, I include the identity in there as well. It's pretty clear that that's a group, okay? And it's smaller, all right? It's smaller. How would that change things? Would I get a different collection of equivalence classes? Okay, well, actually I wouldn't, okay? Because think about it. Now all I'm doing is rotating I'm rotating in the clockwise direction all the way around. This is still a group. Like for instance, let's just think about this. What is the inverse of pi 2, 90-degree rotation? Well, it would be 270-degree rotation because that gets me back to the identity. What is the inverse of 180-degree rotation? Well, itself, right? That gets you back to the identity. Okay, and of course, if I compose any two of these, I'm just going to end up with another rotation. Okay, so meets all the requirements of being a group. Technically speaking, this is called a subgroup of the original group. Okay, that's using abstract algebra language. But all I've done is I've restricted to the rotations here. And if you look at these equivalence classes, none of them really change, right? It looks like we get the same equivalence classes if you just think about it for a minute. And that's kind of alarming at first because you think, well, wait a minute, how is Burnsides theorem gonna still tell me that there are 6 things, okay? Well, let's see, so Burnsides theorem, okay, so says that the number of equivalence classes here, okay, which we know is going to be 6, is going to be 1 over 4, okay, 1 over the size of the group. And then what I have to do is think about the number of things, the number of these colorings that fix, or the number of colorings that are fixed by pi 1. Okay, so how many colorings are fixed by pi 1? Well, all of them, okay? So all 16 of these things are fixed by pi 1. This right here is psi of pi 1, okay, plus, okay, how many colorings are fixed by 90-degree rotation? How many of these colorings are fixed by 90-degree rotation? Well, certainly C1 is, okay? Is C2? No. Is C3 fixed? No. Is C4? No. C5? No. What about C6 through C9? None of those are fixed by 90-degree rotation. C10 and C11? No. Those aren't fixed by 90-degree rotation. What about C12 through C15? No. All of those give different things if I rotate them by 90 degrees. So it's just 2, okay? So that's what psi of pi 2 is, okay, plus. Oh, and by the way, let me just mention, some people in either office hours or class meeting time mentioned that it would be nice if I sort of explained some of the notation in this computation at the end of this section of 9.2. And so I tried to do overbraces that were more explanatory than the ones that were in there. So I corrected some of my notes over there for your convenience. What about 180-degree rotation? How many things get fixed by 180-degree rotation? Well, C1 certainly does, as does C16, so that's 2 things. Okay, anything else? Well, C2 through C5, nothing's going to happen with that. Or actually, they aren't going to be fixed by 180-degree rotation. That white vertex is going to go to the opposite corner. And I'll be able to distinguish, like C2, for instance. So C2 through C5, none of those are fixed by 180-degree rotation. C6 through C9, none of those are. C10 and C11 are both fixed by 180-degree rotation, but C12 through C15 aren't fixed. So really it's just C1, C10, C11, and C16. So there are 4 things that are fixed by psi of pi 3, okay, plus. Okay, what about 270-degree rotation? Well, that's just backwards rotation by 90 degrees, counterclockwise rotation by 90 degrees. So that's just going to be 2 also. Okay, so that's what psi of pi 4 is. Okay, close parentheses. And what do we have here? Well, that's, 16, 20, that's 24 over 4. Which is 6, as it should be, okay? So even though we changed the group under consideration, we still got the same result. That's sort of the beauty of Burnsides theorem. We were able to restrict the group that we were looking at to just rotations. And that made us nervous because you would think, oh man, I just changed the group itself that I'm letting operate on this. And the equivalence classes didn't end up changing, but certainly the count of the number of equivalence classes should change. And it doesn't. Nothing we did depended on the group that we were looking at, okay? We still get the correct number of equivalence classes here, as we would expect. As I'm scrolling downward here, I just wanted to point out that this is what I changed in the notes This is on Canvas, so you should have access to this. So this was the computation for that same problem we were just working on, but when we had all 8 of the symmetries accounted for. That first summand is phi of C1, and so I'm just counting, I'm saying pi 1 through pi 8 fix C1, so that's why phi of C1 is 8. And then I'm saying that pi 1 and pi 7 fix the second coloring. So that's why phi of C2 is 2. And I've written that I put those little over braces on all of those. And then similarly down here, I did that. So here, instead of using phi, right, counting the number of permutations that fix a given coloring, I'm counting the number of colorings that are fixed by a given permutation. So how many things does pi 1 fix? Well, everything. How many things does pi 2 fix? Well, 2, and then etc. Right? So we have that as well. I just wanted to point that out. That's in the notes for your convenience. But let's go down here and do a new problem. Okay, so this one right here. It says 15 balls. I'm gonna go up here so we can start working this out up here. 15 balls are put into a triangular array as shown. Okay, as shown, well, I'm gonna have to actually show you. So it's gonna be there's 5 here, and then there's gonna be 4 right here, and then 3, and then 2, and then 1. That's 15 balls right there, okay? So, 5 plus 4 plus 3 plus 2 plus 1 is 15. Okay, so 15 balls are put into a triangular array like so. How many different arrays can be made using balls of 3 different colors if the array is free to rotate? Okay, so again, what do? Well, we kind of let T be the collection of all, what's the size of the colorings? Now remember, before we were just doing 2 colorings, but there wasn't anything special about the number 2. Once we did all of the theory, we should realize now that, oh man, actually just having black and white vertices, I could have had a 3rd color or a 4th. I would have to think about how these things move around and what things are equivalent, maybe a little bit harder, but that's okay. The theory all goes through. Everything that we did in Burnsides theorem still goes through. So T is going to be the collection of all colorings. Okay. All colorings, okay, without accounting anything about, whether they're actually equivalent or whatever, okay? And all we're talking about is freedom to rotate, kind of like what we just did in the last problem. Last problem, we said, well, what if I don't want to allow flipping around reflections? What that basically does, if I only allow rotation, that basically means I'm only letting that thing kind of spin around in the plane, and that's it. It's only allowed to kind of spin in the plane. It's not allowed to enter into 3-dimensional space. That's what it would have to do if I was going to reflect it somehow, okay? So T is the collection of all colorings, but this time my group is simply going to be a group of rotations of this thing, okay? So like the point of rotation, here, let me just kind of indicate that. Okay, the point of rotation for this is going to be right in the middle right here. So this is the rotation point right here. This is the rotation point. And how many colorings are there going to be total here? Well, the size of T. Okay, the size of T, think about this for a minute. The size of T is going to be, if I can color any of the balls in this array with any of 3 colors, then technically speaking, I can go to any one. I have 3 choices. It's going to be 3 to the 15th. 3 to the 15th. And what's my group? Well, okay, let me just say there's the identity. Okay, there's the identity. And what other, you know, what other group elements do I actually have here? Okay, well, first of all, you know, I can draw these things like this. Notice that, you know, to go from here to here, that's 120 degrees, okay? So it looks to me like the rotations, if I'm only allowing rotations, then there would be one permutation, which would basically be a 120-degree rotation in the clockwise direction. And there would be a permutation, which would be 240-degree rotation. A 240-degree rotation. So the group only has 3 elements in it in this particular case. Okay, so again, here I'm going to write this over here just for our convenience. So G is the set pi sub E and pi sub 120 degrees and pi sub 240 degrees. Okay. Okay, so I have those things. And of course, the size of the number of colorings is 3 to the 15th. And now I have to figure out what's going on with this. Okay, so let me erase some of this junk just so I can do some stuff over here again and not have to get out of this screen. Okay. So now I need to think about, if I'm going to apply Burnsides theorem, I need to think about how certain colorings are going to be affected by these permutations. Okay, so let's just kind of think about this. So if I have one of these 15 ball arrays, so think about it. What sorts of things are going to be fixed by this? Well, I want you to think about this thing this way. Look, if I rotate this triangular array about this point that's right in the middle, I just kind of made that point again, that's my rotation point I'm going to spin around, then what would have to happen? I mean, think about it. You know, this right here, see these 4 balls right here? Those 4 balls would then rotate to these ones. Okay, so these ones would go here under pi 120 degrees, and these guys would go here. Okay, etc. Right? So this would go here, and this would go here. Yeah. And similarly, these balls in the middle would just kind of rotate into each other. Okay, those little balls in the middle would form their own little 3 cycle. Okay, so for a permutation, so let me just kind of write down what I'm thinking here. For an arrangement of balls to be fixed by the 120-degree rotation, okay, what would have to happen? Well, you know, all those 4 balls over there on the left would have to, you would have to have the exact same pattern as those 4 balls on the right, which in turn would have to have the exact same pattern as those ones down there, okay? So it looks like I would have basically, I would be free here, right? So here I would be free to assign a coloring. Like I could do red, green, blue, red, or something like that, right? So maybe I'll do a couple of colorings here. So maybe, you know, maybe I go like this. So maybe this one's yellow. If that one's yellow, this one would have to be yellow, and this one would have to be yellow. Okay. What about, let's use green. Okay. Okay. If this one was green, then this would have to be green, and so would this one, okay? And maybe, maybe I have a green one right here also, okay? Then this would have to be green, and this would have to be green, okay? And maybe the third color is just red, okay? So this one, if that one's red, then that would have to be red, and that would have to be red. If I want this thing to be fixed, right? If I want this thing to be fixed by 120-degree rotation. So I would be free to choose that little blue rectangle box of balls. So, I would have 3 times 3 times 3 times 3 choices right there. Okay, and what about this? Well, in here, look, if this thing right here were green, and then that would have to be green, and that would have to be green, okay? So this little triangle in there, I would be free with also, okay? So I would also enjoy freedom, but really only with one ball here, okay? So let me just kind of, oops, I turned off my pen, sorry about that. Only with one ball right here, so I would be free with that one. Okay, so I could choose one ball in like the middle triangle, and I could choose a ball. I have 3 choices for the first, second, third, and fourth ball in that little rectangular block. So all this to say that psi of this permutation, right, the number of colorings that are going to be fixed by 120-degree rotation is equal to, okay, I have 3 times 3 times 3 times 3 in that blue rectangle, and then I just have 3 choices for a coloring for one of the balls in the triangle in the middle. And the other ones would have to follow suit if I want to get fixed by 120-degree rotation. Okay, so what is this going to be? That's like 3 to the 5th. 3 to the 5th colorings. Okay, and what about well, here's an easy one. What's psi of the identity? How many colorings are fixed by the identity? Well, all of them, all 3 to the 15th of these things, okay? Then finally, what about 240-degree rotation? How many things are fixed? How many colorings are fixed by 240-degree rotation? Well, the argument is, look, rotation by 240 degrees is the same as counterclockwise rotation by 120 degrees. So the argument's the same as the 120-degree case. And so we have 3 to the 5th in this case also, okay? Hopefully that kind of makes sense to you, okay? So that means that what? Look, by Burnsides theorem, the number of truly distinct colorings, if all I'm allowing is for this triangular array to rotate in this way, is going to be 1 over the size of the group, which is 1/3, times psi of pi e plus psi of pi 120 degrees plus psi of 240-degree rotation, okay? That's what Burnsides theorem says, okay? So that being said, that is why we end up having this formula down here. All of that argument that I just kind of drew up there is what's going on here, okay? 1 over the size of the group. So let me just kind of put a color right here. 1 over the size of the group. And then you have to add up all of the psi values for the things in the group, okay? And you could divide everything through by 3, and you get 3 to the 14th plus 2 times 3 to the 4th. So there's really 4,783,131 truly distinct, rotationally distinct colorings, okay? That's amazing. I mean, That's a lot of colorings, yeah. And we were just able to knock that thing out in a hurry like that. I mean, who would have predicted such a thing? It's fairly amazing. Hopefully that's interesting to you. Okay, because I really kind of hammered you last time with a nice long lecture, I think I'm going to leave it at that for now. Really try to understand that picture, reimagining of Burnsides theorem that I drew earlier. I think that will be very, very helpful. That will aid your thinking in more ways than you might imagine. Really understand the fact that we could vary the group that we're working with. The number of colors I have available, I can also vary. I had a lot more freedom than I realized there. And we're going to really be taking advantage of all those things and really try to understand that triangular array example that we just did. That's a fairly simple application of Burnside's theorem, but we did something very surprisingly difficult in a simple application of that formula we came up with. I mean, try to think, how in the world would you have counted those colorings? That would have been a nightmare. And we were able to just knock it out in a hurry. It's amazing. Now, just to kind of foreshadow where we're going, we're next going to talk about something called the cycle index. And the goal is going to be, look, we've kind of been notice in that example, we had to think pretty hard about, man, how many colorings does a particular permutation fix? That doesn't necessarily seem like it's a very easy thing to pull off. Well, did you notice how we were kind of having to think in terms of cycles there? We were having to think in terms of what stuff was cycling into what stuff that was cycling into other stuff. Turns out that's going to be the key to computing psi of pi in a systematic way. We're going to systematize even that computation. So not only does Burnside's theorem give us a way of counting something that at first didn't seem like it was going to be possible, namely the number of equivalent, the number of truly distinct colorings when we had a bunch of different sized equivalence classes potentially. So Burnside's theorem told us how to do that. But we're even going to be able to systematize the way that we compute the things that are in the sum of Burnside's theorem. And we're specifically going to focus on psi of pi. So you give me a permutation, I need to figure out how many colorings are going to be fixed by that permutation. We're going to be able to systematize that. We're not going to have to be super clever eventually. And it's going to have to do with the cycle structure of the permutation. The cycle structure is going to be the key, which is why I spent so much time a couple lectures back hammering home writing permutations in cycle notation. That's going to be the key. All right. I think that's all I have to say for now. So please come in, ask questions, stay engaged. Man, I hope you're enjoying this stuff. This is some exciting climactic moments in the class. I really love this material, especially. It seems to just be a nice climactic point where all the ideas we've been collecting together are brought to bear, and we reap some good fruit from all of our labors. All right. Have a good day.